Let's just dive right in. Right now, at the very heart of modern physics, there is this fundamental clash that has quite literally kept the greatest minds awake at night for decades. See, we have these two amazing rulebooks for how the universe works. One rulebook perfectly describes the massive, heavy things, like planets, stars, and galaxies. The other rulebook, well, it perfectly describes the tiny things, like atoms and particles. But here's the catch. These two rulebooks completely refuse to work together. So today, we're going to explore why a major theory that's trying to solve this, called loop quantum gravity, might actually be breaking under pressure. And we're going to look at it through a really fascinating new lens. Here is our agenda for the explainer today. 1. The quantum gravity problem. 2. Triune harmonic dynamics explained. 3. Measuring the structural pressure. 4. Falsification and testing parameters. And finally, 5. Real-world science implications. Section 1. The quantum gravity problem. The missing bridge between the large and the tiny. Okay, so we've got a massive existing understanding problem here. Picture this. On one side, we have general relativity. That's Einstein's famous theory, right? It tells us that space and time are like this smooth, continuous fabric. When heavy things, like planets, sit on this fabric, it bends. And that bending is what you and I feel as gravity. But on the exact opposite side, we have loop quantum gravity, or LQG. Now, LQG says, hold on, if you zoom in close enough, space isn't smooth at all. Instead, it's made up of tiny, individual pixelated chunks. They usually call these spin networks. So here is the absolutely crucial point. If space is actually made of tiny pixels, then when you zoom out, those pixels should blend together to look like that smooth fabric of gravity we see in the real world. But scientists are stuck. They literally cannot find the math to zoom out from the pixels and get that smooth picture back. The bridge is just missing. Section 2. Triune harmonic dynamics explained. Diagnosing the stress. So how do we understand the strain on a theory that's stuck like this? Well, to diagnose the stress, we're going to use a really brilliant tool. We turn to the work of Kevin L. Brown. He's the researcher, inventor, and author behind this concept. Brown has spent his life searching for a universal pattern behind reality itself, and he noticed something amazing. From the way atoms bond, to how our cells grow, to how entire galaxies form, everything follows a universal rhythm. He said, the universe evolves in harmony, and that harmony speaks the language of three. Change isn't just random, you guys. It follows a harmony. Brown called this triune harmonic dynamics, or THD. Let's break that down into plain English. THD is basically a testable framework showing that all change in the universe follows a repeating 3-6-9 pattern. It's a cycle of birth, stress, and resolution. Think about it like learning to ride a bike. First, you get on the bike, that's the birth of the idea. Then you wobble, you struggle, maybe you even fall off. That's the stress or the pressure phase. Finally, you figure it out and you ride smoothly. That's the resolution. Kevin L. Brown's research shows that scientific theories, just like everything else in nature, have to go through these exact same phases of evolution and testing. Let's actually apply this directly to loop quantum gravity. Here are the 3 steps of THD. Step 1 is emergence. A new idea forms. For LQG, this was the super exciting idea that space might be pixelated. Step 2 is pressure. The idea gets tested and stressed out. Step 3 is integration, where the idea either adapts and succeeds, or it flat out breaks and needs to be replaced. So where are we now? Well, the THD hypothesis tells us that loop quantum gravity is completely stuck in step 2. The pressure phase. It's under massive stress right now because, despite years of brilliant mathematicians working on it, it's really struggling to connect those tiny pixels to the smooth space we actually observe in reality. Section 3. Measuring the structural pressure. Testing the strain on the theory. Okay, so how do we actually measure the stress on a mathematical theory? I mean, we can't exactly put it on a physical scale, right? We need what are called validation test mechanisms. Think of these like red warning lights flashing on the dashboard of loop quantum gravity. First up, we look at anomaly frequency. That just means unresolved problems are piling up. Scientists keep hitting the exact same roadblock over and over again. Second is model divergence. This is the big one. It's that stubborn gap between the pixelated geometry the math predicts and the smooth space that we, actually live in. Third, we use instability metrics. Look, a strong theory makes strong, unique predictions that we can go out and test with telescopes or lasers. But a pressure theory, it relies on weak predictions or just constant wild guesswork just to stay alive. Let's compare these two states. A low-pressure theory is a healthy theory.
It gives us clear predictions, it smoothly bridges the gap between different ideas, and it relies on hard, testable facts. On the flip side, a high-pressure theory has missing variables. It needs constant revisions by scientists just to keep it from falling apart. And crucially, for LQG, it completely fails to produce the smooth space we know is out there. So based on Kevin L. Brown's THD metrics, loop quantum gravity is currently ticking every single box in the high-pressure category. It's a theory under immense strain.
Section 4. Falsification and testing parameters. How do we know if THD is wrong? Now, I want to pause here for a second and ask you, how do we actually prove this THD hypothesis wrong? Because good science is all about falsifiability. What exact evidence would clear loop quantum gravity of this high-pressure failure label?
Well, here are our strict falsification parameters. The THD hypothesis about this failure is proven totally wrong if loop quantum gravity can pull off three things. First, if it successfully finds that missing bridge and recovers smooth spacetime from its pixelated math without any extra guesswork. Second, if it confirms unique quantum geometry signatures. That means we actually find physical proof of these tiny space pixels using our advanced instruments. And third, if it predicts observable effects before we actually measure them in the real world. Plainly stated, if LQG connects the dots and becomes a reliable, predictive tool, then the THD pressure hypothesis fails. It's a highly testable claim, which is exactly what we want in science.
Section 5. Real-world science implications. What happens next? So why does all of this actually matter to you and me? Why should we care about some abstract mathematical chalkboard problem? Well, because it dictates the entire future of human discovery. If we can use THD to prove a theory is just stuck in an endless pressure phase with no bridge in sight, scientific institutions can shift billions of dollars in funding toward more testable, promising theories. It helps the brightest minds in physics avoid wasting their entire careers on models stuck in endless revision loops. And as for future discovery, it forces us to look elsewhere. It forces us to start searching for entirely new, deeper rules about how space actually emerges. Which really just leaves us with this final, thrilling question. If our current, most popular theories of quantum gravity are failing the THD pressure test, what entirely new harmonic rhythm of the universe is out there just waiting for us to discover it? If the universe really does speak the language of three, like Kevin L. Brown suggests, then maybe the true nature of spacetime is way more musical, structured, and beautiful than we ever even imagined. Thanks so much for joining me for this explainer. Keep questioning, keep learning, and I'll see you next time.